Okay, morning everybody. So glad to come back and start another class. Let me pull my computer here. Good to see everybody. And looks like we lucked out this time and didn't get much impact from the hurricane. I hope everybody is the same case here, right? So let's begin our exciting journeys of polymer physics. It's going to be different with the other two classes you guys studied in polymer chemistry. So everybody has access to the canvas, okay, right? So if you have problems to reach that, let me know. So I want to begin this class to ask a few questions to everybody first. The question is, why? The question is, again, why? Why you need to learn polymer physics? Why someone tells you you have to do it? This is the number one question I ask my students to understand at first. I'm sure you will know how to do it. And I'm sure you will know what to do with the class once you learned it. But I want to begin with the important question. Why you need to learn polymer physics? Not because of the graduate school said this is going to be on your curriculum. I want to make it clear. So anybody want to give it a try? Why we need to learn polymer physics? Anyone? Oui?
Well, I guess it's the same reason you need to take, thermo or mechanics to do CAD/CAM work.
I think that's part of the reason, but I haven't speak to the powerfulness of the polymer physics that you guys will learn later on throughout this year and 2 more courses next year. The polymer physics, let me tell you guys the ability of polymer physics. Let me give you a few examples I think historically make huge impacts in our lives around here. So one of the major events made a big impact for me. When I was very little, I was always dreamed of to be astronauts. Same for my little son, 5-year-old. He plays all the kind of different Lego toys for the space scene. I was the same one. But when I was little, I heard about there's a tragic for Challenger space shuttle. That was a very, very bad one. And we lost several astronauts because of that catastrophe. And later on, people start to look into why the space shuttle was burst into explosion just a few minutes into the space, or burst into the launch. It turns out to be a polymer seal was the reason to blame. The polymer was experiencing very, very low temperature, so it's lost its ability to perform what the role needs to be performed, which is an elastic sealant it's supposed to do. So a lot of those tiny details could cause a lot of big problems, right? But that is one, if someone in the engineering team was trained at USN, was being a part of NASA team, that might be avoided. And I hope you will be one of those guys down the road, being a big petrol company or being an engineer somewhere. You can apply some of the knowledge we learned today. That's big picture-wise, okay? Polymer physics can solve other problems that chemists may not see, but they would be critical. I want to dial a little bit back, think about what we can do with polymer physics. So fundamentally, let me say what we're going to teach as a big picture for the polymer physics. So we're going to cover 2 very important topics through me and Dr. Simon first, then Dr. Nazarenko. So we're going to cover everything from structure. What I mean structure is I'm fascinated to know how does these polymers look like structure-wise. Structure, I mean nanoscopically, not just looking at this fabric made of nylon, but I want to zoom in billions times to see how these molecules of nylon are being packed with respect to each other, okay? We're going to learn everything about polymer structure, which is the topic of this September. We're going to learn polymer conformation, polymer chains. So these are a little bit abstract, but fundamentally what we're going to do is to teach everybody, if you are a nanoman, everybody loves Marvel Studio superheroes, right? There's Ant-Man. I want to create a nanoman here. So imagine you are the nanoman for the next month. You're going to be able to see scale size on the nanoscale. You will be able to see how the polymer chains looks like a giant forest around you, how they pack with each other, and how these nanoforests will impact their fundamental properties on the bigger scale, which is something we can see at the millimeter or bigger scale, okay? We're going to draw the some links, but first we want to know how to quantify a polymer chain if we're speaking about polystyrene. Your polystyrene and your polystyrene, your polyethylene with someone in India, someone in China, someone in England, someone in Germany, are they talking about the same? So how can we unify this and understand conformation of the polymer chain? And different polymers as well, not just the polyethylene, polypropylene, etc. So we're going to go through these. Coming from a fundamental level to understand how does these polymers look like at nanoscale. So structure is something we're going to cover. And then we're going to cover polymer solution. How does the polymer chain behave in solution state, and how does the polymer mix? This is probably most useful knowledge you're going to get, because the first part is good to help you start to understand polymer physics. But a lot of useful things is come into the solution process and the phase behavior of the polymer. Polymer melts, polymer solutions will help you understand how does these different polymer behave in solution state, and how you can understand their rheological property, etc., etc. So that's what we're going to cover in October. Everything relevant to solution, because that's a big part of the polymer physics. Okay. Then the last part, but not least, in my role, I'm going to also teach everybody how we can apply some of the fundamentals we learned for these first part of it, and understand a very important phenomenon in polymer, which is rubber elasticity. So one of the things that other material cannot replace is a rubber, which is represented in one of the important discovery for plastics. Okay, a lot of metals, they're hard, they're rigid, they can use in structural material such as car frames, bridges, buildings, but there's not a lot of material behave uniquely like polymer plastic, such as rubber gasket. So we're going to apply what we learned fundamentally. Then you guys not only going to be learning something structural or stationary, what I call it. So a lot of phenomena is response to the time. I'm not stationary. If I stay still for a long time, that means I'm probably is dead. Polymer is not that either. It moves around at different time scale. What do I mean time scale is what we live is in the time scale of seconds. We can see things happening on seconds, hour time scale. But a lot of interesting things happens at much faster time scale, milliseconds or nanosecond time scale, or even longer time scale. So what are we going to learn next chapter, which is next spring, you guys will learn from, based on my teaching, you're going to see how I look the shape, size of myself, and see how fast I move, which is how fast the polymer moves, okay? So 2 parts. Structure-wise, we're going to cover everything this semester, and dynamics is another important part. See how they move and how fast they move, how they move with respect to each other. Then there's another important part of the polymer physics. Combining these two, we want to understand the morphology. So Dr. Nazarenko can teach you, or everybody, all about solid state morphology of that. How does polymer crystallize? How do they behave in different temperature with respect to important concepts such as glass transition temperature and melting behavior. So combining all these, you would have a very, very solid knowledge to tackle a new material. Let's say, come back to the other day, I think I asked a question about what if we want to design a new iPad case? What property you want to have? Toughness, softness. You need to play a little bit of trade-off between these. Of course, I don't want to deny the polymer chemistry is important, and they're continue going to be important to create a new material. But I understand that those newly developed materials' physical property are going to also help you to understand how you can optimize the material and get it into better property. Let's say I see that your chain is not entangled because your chain may be too rigid. Then you can think about what we can do to engineer them into different direction. So combining all these, I'm sure you guys will be able to solve upcoming challenges faced by the human society. Okay? So that's a big picture of why. I want to make sure everybody understands why you want to study polymer physics before you do anything else. If you don't have a clear goal, it's going to be fuzzy. Why we need to sit in this classroom and learn this and that. Okay. So now coming back to this particular lecture, we're going to talk about everything about structure. So when we speak about structure, what comes into your mind when you think about structure? Can someone give me some ideas, some thoughts, some hints when I speak about polymer structure?
Branching, cross-linking.
That's a good one. Let's talk about different architecture, right? Cross-linking is an important approach people develop in new material. We will cover a little bit there in the later part, probably sometime in November. Chantal?
Number of breaking units or molecular weight.
Wow, that's speak to the importance of polymer. That's separate us with all the other material. Is the connectivity of polymer. Let's tell everybody a little bit background and story about polymers. Is when people discovered polymer, I think I mentioned nobody was believing their existence of polymer about 100 years ago. So people think they're just some small molecule, somehow non-covalent, also have some interaction, causing them to behave slightly different with other material. But nobody knows why. And there's no cool techniques like high-resolution microscopy. You can actually see a single chain. Nobody can see it. Every measurement is indirect. Some of the early calculation to viscosity. So you can look at how does viscosity changes when you polymerize it. And one of the characteristics of one polymer solution is it's molecular weight dependent. Even you have the same polyethylene at different molecular weight, their melt, their solution property was totally different, right? So that's a very good call. Any other guess when we think about structure of the polymer?
Molecular interactions and intermolecular interactions.
Yeah. I think that's another part we want to cover a little bit in the later part. How does different interaction impact your polymer core, right? Polymer chain. So I think we're going to begin the class by introducing some of the fundamentals of polymer physics, is how we should visualize the polymer chain, okay? How we should understand the polymer chain looks like in three-dimensional space. This maybe sounds simple. Polymer is just a chain. But how do they physically oriented with respect to itself within one polymer and how does the polymer chain behave if it's surrounded by other or surrounded by solvent molecular, is something of a great start for us to begin learn polymer physics. So that's all about what we're going to do in September, is to understand the polymer conformation for a single chain. We're going to start with simple. We don't want to complicate too much. Let's just imagine a very simple polyethylene. That's probably the most simple molecular in polymer. It's just made of varieties of ethylene group, CH2 repeating unit. And our question to begin the class is how we should visualize and understand a single polyethylene polymer, and how we should ascribe some physical terms to describe your polyethylene versus my polyethylene. Okay? What I mean by your polyethylene is how molecular weight, for example, impact its conformation in size. So I want to ask a very simple question. Polymers in the polymer chemistry, let me see if they have chalks. There's one. Oh, there's more there? Okay. Perfect. So, well, if I draw a polymer, how should I visualize it? It will be somewhere looks like this, or it will be more look like this, or it will be more dense. We're going to learn a little bit on these, and we will teach everybody how they behave physically. So let's start with 3. It doesn't count to your school, but how many of you think it's going to behave like A? Raise your hand. Let me just see. Nobody think polymer coil will behave like A? Anyone? It won't hurt your score. I just do 1 C. Okay, 2. Good. So we have 2 votes. How about B? Oh, that's majority of you. I would say maybe about 17. C? What? How could you vote twice?
It depends on what solvent. It could be any of the 3. That's a good point.
That's a very good point. So we will learn, okay? But this is a good start. A polymer, hypothetically, although in the structure-wise we typically draw CH2, let's use polyethylene as an example, right? So on and so forth, or we can basically write this way. So it's not a straight chain like this shows. Why? That's something we're going to learn about in the next 2 weeks. Why it's not something even more extreme is going to be perfect straight or elongated in this case, or B and C. Of course, you have the possibility to go into all the states. Depends on how you process or how you provide any stimuli to your material. There can be force. You can do mechanically something happening to your polymer, or you can do thermal, you can do magnetic field, you can do electrical field as well. All these could impact the conformation. But more commonly one is the interact with solvent, okay? So we're going to come into that part. So I always wanted to start with something simple and tangible that everybody can see and visualize. So let's give a little bit example. Let's say I have a 28K polyethylene. I want to ask everybody, this is a molecule, let me write it more straight, kilodalton, KDA, 28. Typical polymer ranges from the lower end going to be a few kilodalton, high molecular weight going to be a few millions or even higher. But for most of the chemistry you're going to do in a typical synthetic lab is going to be on the tens kilodalton range, okay? So this would be something you typically deal with. All right, I'm going to ask you something again. If majority think it's B, I want to ask you how big this coil, if we look at it, if we have a ruler, we put it there, is it going to be 1 nanometer or 10 nanometer or 100 nanometer or 1,000 nanometer? All right, this is getting a bit tricky. If you win those, I'll get you a donut next class. All right, you got a fair good chance, right? Most of you get this right. So, most the closest, okay? It's probably not going to be exactly 10, but let me give my better chance. Let's call E 0.1 nanometer. All right, let's start this. 2 volts for, you can't vote twice, okay? Let's be fair to me and for yourself. How many of you think it's about 10 nanometer? 1, 2, 3, 4. Remember your vote, okay? Because next time when you get donut, you need to tell me. I won't bring more than the number I show here. So C, 100. 1, 2, 3, 4, 5, 6. Majority thinks it's this. So we got 9. So we should have a few of them at D. Okay, we got a 1. Anyone at E? You guys know this is not the right one. Smart. So let's do a little bit of understanding of how big this polymer chain would look like this. We're actually going to need to introduce a little bit of concept, but we can do it in this later part of this class. So let's take a look at this particular case. So if let me try to find something. Perfect. Unopen the box of cable. Perfect for me to demonstrate the polymer. So your polymer coil will not behave like this, because unless there's supernatural force, your polymer will not coil up. There's a special case, of course, you can design the polymer to go around the circle. But this would be something we call the longest length of your polymer, because that's as long as you can pull it. We have a term for it. I will tell everybody just in a second. This is called contour length. We typically call this as LC, means contour length, which is roughly how long your overall size of your polymer chain is, okay? So contour length is going to be the longest length of your polymer. B? Now this B is a little bit tricky, because pretty much like this. Maybe not perfect, but this is a good way you can see how the polymer coil, if you zoom in to the nanoscale, this will be roughly the 3-dimensional space you're going to see the polymer. Okay, so how do we describe it? It's harder, because we can't put a ruler just to measure it from here to there. If you invented one, let me know, because I can't do it. I don't have the ability to, let's say, has a microscopy to look at the single chain. I think the latest development probably using the cryo-EM can do that, but it's really hard, okay? So commonly, we can't do that, so we need to design a new technique and a new ways to describe the polymer coil. Or here, so I'll teach everybody today. So this is called, either you can use a radius gyration, which we won't touch today, but later on we will teach, which can be measured by light scattering, a technique that has been commonly used to measure the coil size. We're going to teach all the detail about light scattering actually by Dr. Simon next year, but I'll teach everybody a little bit of basics about it so you can understand. So you can shine a laser to be more accurate to your polymer and look at how the laser is being deflected, and you can understand how big your coil is, okay? You can measure it. Shante? It is part of the detector in the GPC. So GPC take advantage of this technology in the detector area, but there's also other technique. Okay, you can use to measure. So you can use this to understand the coil size. But still, for the polymer physics, someone like me, when I describe it, I want something more simple and easy to understand. So what we invented is a very simple term we called end-to-end distance. So we just need to count where you start your molecular, where you end, what's the average distance. You heard about me, average distance. Because this would describe how big your coil indirectly, where you start, where you end. So let's do a little bit calculation later on in the class. And I'll take picture of it because we won't be able to answer all of this today. But I'll give you guys some hint how to look for this answer. Okay? So end-to-end distance is another parameter. We typically write as R. EE means end-to-end. Okay? So this is a parameter we can use to describe. So as one of your classmates said, C is also possible. When are we going to have the polymer comes into the shape of C? I need to really squeeze it hard. I don't want to break the line, so I'm not going to do it. But you can imagine if you put it in the hydraulic press, you can really squeeze it into as tiny as possible. Then your size also shrink quite a bit because the polymer will occupy 3D space. So in the textbook, if you read the Polymer Chemistry, I think people give a very good example how different size with respect to each other it can be. So smallest case, for the same polymer chain, from the smallest, it can be, if we have to put a real size, if we squeeze everything, it's going to be as small as a tennis ball. Okay? Think about that, or even smaller. When we have end-to-end distance, we're looking at a football size, a football size, and when we further pull the polymer chain, it's going to be expanded by another factor of 10 to 20, depending on the molecular weight. So as you can see, size scales could vary dramatically for a given polymer chain. And I can guarantee you, your physical property will be different depending on if your polymer is in extended states, if in the semi-colloidal states, or let's just call it a Gaussian colloidal states, or it's in the compact or globular states, which happens if you precipitate your polymer in a non-solvent. You basically squeeze all the polymer. Okay? So different time, same polymer, different physical property you will get. Isn't that amazing? This is truly like an Ant-Man in the Marvel movie for a polymer. It can shrink itself. It can expand it. It can be as big as a normal person. It can be shrink to the nanoscale. Okay, so now let's begin the real part of today's lecture. which is, it's a little bit long introduction, but I hope I convinced you why the polymer physics class is important, why we need to start with the structure, okay? And remember that. So let's take a look at what's some of the importance in the polymer, describing a polymer chain. We alluded that there's two effects coming into play, and probably more. How big the size is, right? So let's take a look at this slide. This describes you importance of something interesting is how we should understand first a fully extended chain. This is the most easy one if we look at a fully extended chain. And intuitively, you guys can all understand. When the polymer is elongated, this depends on how many repeating units in it. If it's just a little bit repeating unit, it's going to be short polymer chain. If n goes up, how does that length increases with n? It scales linearly, right? So think about if we hold each other's hand to be a long straight chain. If we add one more person, the length is going to be increased, same as one more person length. So this can be described by very simple term we call degree of polymerization. So if you haven't heard about it, you will learn this in the next few lectures in the polymer chemistry, I'm sure. This defines by this very simple equation. So molecular weight of your home polymer chain, which you can measure by GPC or light scattering or a variety of technique. So let's use this example again. So 28 kilodalton polyethylene, 28 is the whole molecular weight, chain molecular weight. N0 stands for repeating units molecular weight. So that means how big each repeating unit. So in this case, repeating units, I should not write this way. Okay, it is. So to be more exact, this is repeating units. This coming from ethylene monomer. So dP corresponding to total molecular weight and divided by M0. So what is the dP for 28 kilodalton? 1,000. Very good. So that's about 1,000. That means there's 1,000 of these repeating units going along. So length of fully extended chain. There's two ways we can understand this. There's two assumptions. Fully ideal chain versus a semi-ideal chain. Let's talk about fully ideal chain. In the fully ideal chain, all the bonds can be flexible. So we sometimes call it free joined chain, which we will cover a little bit today's class and next class. Free joined chain, what does it mean? That means if I'm in the chain, this is another chain. There's a bond that links to us. And in normal cases, the bond has a specific angle. That means this arm, this bond cannot be rotating in any direction, okay? Right? There's a certain fixed angle to it. Let me get an eraser and show what I mean. So if we have, looking at I should probably draw it three-dimensionally. This will be represent a methane molecule. You have CH4. And this forms a perfect pyramid structure. So if you look at this, there's a pyramid structure where carbon is in the center. So there is a certain bond angle. This bond cannot rotate at any angle you like in real case. But in the polymer physics side, we say we want to start with simple. what the simplest term is, let's assume there's no restriction in the bond. So if I have this carbon-carbon bond, this bond can rotate at any angle if it like, and can be rotated in any direction equally. Total freedom, three-dimensional space. Okay, so in that case, then if you can pull the polyethylene, it's going to be a straight carbon-carbon chain, right? So how long is the polymer? It's going to be CH2, CH2. We said it has a dp of 1,000. So what would be the contour length for free joint chain? So all we need to do is to understand how long are each repeating units. And not too hard. This is the simplest polymer physics problem. So each carbon-carbon bond actually has a given length. It's roughly about 1.54, 0.154. No, sorry. 1.14 angstrom. So that's how long this bond is. If you concentrate from one carbon to the other. So what would be LC for a fully extended one? So that will be 1.54 multiplied by 1,000. Is that right? Did I miss something?
Yes, there's 2 carbon-carbon bonds in the repeat unit.
That's right. Don't forget each of the repeating unit, it has 2, right? So we need to count 1, 2. So there's 2 carbons. 2 carbon-carbon bond within a repeat unit n. So there's factor of 2. So how long is actually our 28 kilodalton PE in lengthwise? So that's about 3,000 angstrom, right? Or 300 nanometer in length. It's a little bit small, but you guys see 300 nanometer. If we increase the molecular weight by a factor of 10, 280 K, then your total length is going to increase by a factor of 10. It's scaled linearly. Think about we hold hands being a long line. If ever we have a really terrible situation, there's a large flood here, we need to hold a hand to rescue somebody in the water. You can count how long my arm is. You can estimate how many people we need to hold hands to reach someone to rescue, right? So if we have 10,000 monomer, that means it's going to be longer than what we show here. We only have 1,000. For 10,000, you can have about 3 microns if your bond angle is 180. But in reality, as I mentioned, carbon-carbon bond in this structure is not as straight as 180. So if you count each carbon-carbon angle, this is about, let's draw this way. It's probably easier. Then you have hydrogen coming about here. So this bond is about 109 degree. So then even if you extend it, there is still some zigzag happens in the backbone. You can calculate based on this simple law of cosines. Very easy. I already did it for you. So you're going to shrink a little bit length. How do you visualize it? A bunch of people holding hands, but you need pull a little bit in. Okay? If you shrink a little bit in this direction, represent this bond influence. Or you're holding hand not straight, but facing towards you, you have 2 people holding hand this way. This is the longest possible length, as I mentioned. But is it possible polymer adopt this conformation?
Kind of.
Almost impossible. There's only special cases they might be closer to that. and not even in the fully extended way. I'll tell you a term you guys probably learned in the polymer physical chemistry class, something called entropy, which we will talk in great detail in October. Thermodynamics, enthalpy, entropy, they're so abstract, but they basically says, in the layman's term, entropy will always go up. Or even more layman's, if you don't do anything, things will get disorder. Or even another level, if I don't clean my dish, my living room, it will get messy. That's just a spontaneous happen. So for a straight polymer chain, entropy is almost zero. So spontaneously, it's going to adopt higher entropy state, which is going to relax back. Okay, think about this. I'm going to do that again. Straight. Polymer chain going to relax back because it doesn't like that. It would prefer to do this way. And this is a fundamental what we're going to learn in this November, how your rubber works. Rubber takes advantage of this phenomenon called the rubber elasticity. Basically, it's the entropy effect. We're going to go into a little bit more detail when we walk into the November time frame. Everything going to relax to more random states, so your polymer will be more coiled. Okay? So it's something we're going to cover a little bit more detail. But if this is a 300 nanometer, that means we probably don't have a chance for this students to be right? We can't be the coil states to be longer than the longest possible form, which is 300 nanometer, we know. So we have 3 left. Which one is right? That's a big portion of this week's lecture and next week's lecture is how we visualize this particular shape of polymer 3-dimensional space. This we already go through. I don't think we need too much discussion on this. We already see the contour length if we consider the bond angle and without consider bond angle, right? So I don't think we need much, except that in their case, this is a 280K, not the molecular weight of ours. So how about the conformation we talked about is fully compact? It's very easy to do as well. We don't need to look at the dimension-wise, measure the bond length, etc. We just consider the density. So the density, how do we do that? If we know how heavy you are and my density, how heavy I am and my density, I can calculate how much volume I occupy, right? Mass divided by density will give you the volume. So this simple concept can be applied. So we know the molecular weight. We can back calculate about how much polymer occupies the dimension-wise. So the answer is this will, if we look at the, sorry for the little bit confusion. So if we look at 280K, your bill will be about 5 nanometer. Okay, think about fully extended is about 2.5 micron. Fully compact is 4.7 nanometer. Although we are off by a scale of 1,000, but remember this is scale by a factor 3. So we're talking about fully compact. This polymer is about 1 nanometer. Okay, so we only left B and C. So which one is right? A is closer to the fully compact. Between C and D is closer to fully extended. So, right? So let's see. We only have option B or C. Let's see which one is closer. Now this part is where we're going to talk about ideal polymer chain for us to make our life easier. the real polymer chain has a few constraints. If you think about a real polymer chain, where did I put this? There is a few constraints. In real polymer chain, or in any real matter, number one consideration is we cannot occupy the same space twice. If this space is being used by someone, you cannot use the same space twice. You cannot sit on the same seat. It's going to be hilarious and embarrassing, right? But to simplify the concept of polymer physics, I will explain why we may want to omit this real polymer chain, start something really fundamental. It doesn't exist in real life, but you can imagine a chain could sit on a three-dimensional space of another one. Okay? And no interaction. The polymer chain do not see itself, which means these parts, they don't interact with each other. If somehow the polymer decides, I'm going to coil back and I'm going to pass here, you can do that. Very simple, ideal chain. And we will also omit all the other factors could come into play, but we will slowly put them back in the later part of the lecture. That is the local stiffness of the polymer chain, the ability to overlapping itself. We actually has two interesting terms in the polymer physics. We call it the random walk polymer chain or Gaussian polymer chain versus a self-avoiding walk or real polymer chain. Okay, self-avoiding walk means you cannot walk to where you already passed. We're going to introduce a few concepts in the polymer chain. So this is actually a good slide to show you, define a few terms so that we can discuss the polymer conformation more easily. What are we looking at? We are looking at a three-dimensional space. Okay, so those three chains are, imagine those are carbon. This is another carbon, and this is going to be the next carbon. Okay, because the bond angle, you have the choice of stay in the plane or like this going to be sticking out this particular projector plane, right? So a few parameters. We need to know the length, which is defined by this bond length L. And this subscription I just defines the bond length number I. Okay? If there's 1, 2, 3, 4, 5, L1, L2, until you reach the add a number I, you're going to label it bond length Li. Next bond will be Li 1 plus 1, Li plus 1. Next one, Li plus 2. Bond angle. So this is sometimes confusing. There's two ways you can look at the bond angle. This bond angle, you can look at from this direction within the bond or the complementary parts, pi minus this theta. Okay, make sure we define which angle it is. In the majority of the discussion, we will use the theta angle to define the bond. So in carbon-carbon bond, that corresponds to 109.5 degree. This is this particular angle. Okay, now we also have other interactions we can omit. So let's start with the simple one. If we don't have any limitation in the bond angle theta, then this is something we're going to do it. We call it free joint chain. This bond can bend in and out, any angle we want to choose. Theta can be anywhere between 0 degree to 180. Fully flexible. If we want to be a little bit more realistic, we know that the theta angle cannot be 0, cannot be 180 in a lot of polymer chain. It depends on what the hybridization of your polymer is. If it's 180 degree, That's going to be fully extended. That happens if you have fully conjugated backbone. Sometimes you have the molecule, you can design theta to be 180. But for sp3 hybridization, which is fully saturated carbon material, this angle always is going to be 109 degree, plus minus a little bit, okay? Let's fix this angle to be 180. I'll bring a model next in the class so everybody can play a little with. We have a real model I sourced so that I can aid everybody to look at three-dimensionally. Now the question is, there's another way, think about it. If you can bend, right? If my arm is fixed at this 109, but I can rotate. If there's any hindrance in rotation, you can rotate 180 degrees freely, which is defined by a second angle. We call it dihedral angle. Okay, so you need to understand what the dihedral angles are. Dihedral angle, if we call it free rotating chain, that means chain can rotate. There's no limitation in dihedral angle. We're going to talk a little bit more detail, but the last restriction, more realistic, is the dihedral angle has a preference. There's a certain angle you're going to rotate and stop there, which defines the steering hindrance. Okay, so this is a great first try for the class. So we're going to stop here. After introducing all the concept about why we need to learn a little bit of polymer physics, conformations, and I think some of you will win either this minority or majority. Let's see in the next class. We will see the answer. Okay? In the next class, what we're going to do is we're going to go a little bit details, introduce how we can use the concept we learned in this simple chain model. Start with the most simple one, free joined chain, to describe how long a polymer chain is. We will learn specifically is how can we describe that coil using some of what we learned and apply this molecular weight to describe how big your coil size is. That's a good starting point. All right, so with that, let's wrap up today's class. So I'll talk to everybody on Thursday this week, okay?